Flood fill. An image is presented by a grid where each cell represents the pixel value of the image. You are also given three integers, row, column, and color. You should perform a flood fill on the image starting from the pixel at the position. To perform a flood fill, consider the starting pixel plus any pixels connected four directionally to the starting pixel of the same color as the starting pixel, plus any pixels connected four directionally to those pixels also with the same color, and so on. Replace the color of all the aforementioned pixels with the color. Return the modified image after performing the flood fill. That is very wordy for a description. What it means is like if you've ever messed around with Microsoft Paint and you put the paint bucket and you click whatever you click on. So if you want to turn, in this example, if you got this bunch of ones, if you click on one of the ones and you want, you have your two bucket. You see, I want to flood fill these ones with two. It'll turn these to twos and it'll leave this one alone because it's connected only diagonally. And the zeros are different. So that's what it means. So this one is going to be pretty simple. It's since you're messing with neighbors and neighbors of neighbors, it's recursive. It's pretty much recursive. Uh, the tricky part is remembering what the original color should be. So like wherever you click, we're noting like, okay, that's the color that we want to change. So there's a couple of ways to possibly do this. One is to do like set things up in this function and make another function that does most of the work. Would it be feasible to reduce it to one function and just like remember the original color outside in a variable? Um, Probably not, because if we were to reuse this function, then we have to have this return by this copy return of the entire grid on every call, which we can do better than that. It doesn't change the theoretical complexities, but it's still a big constant factor. Or does it? No, because it would add another n by n or n by n to each one. Actually, that might be pretty. I'm gonna not do that. I'm gonna go ahead and go with option A, which is making another function. So it's gonna take all the same things as input plus the original color. Okay. So yeah, the idea being, I'm going to first know what the original color is. Maybe I'll change the first one. The work, this is a recursive call. So first you check base. Well, in this one's recursive. So this one we could just do work and then recurse. This one we check base case, do work, and then recurse. Those are the three parts. So I'm gonna go ahead and start on the outside one, I guess. What it's gonna do is, and the original is gonna be, do I need to check? I might check like a base case, quote unquote, anyway in this, just to do bounds checking to make sure these are in bounds. I think that is the way to go. An interviewer, I think, would appreciate, or they'd tell you not to, but okay, constraints. So these, it says it's always going to be in bounds. So that's something to talk about with your interviewer. Just say, hey, do we need to check for bounds, or can we assume that it's always going to be in bounds and like valid for this row and column? Here it says that they're always going to be in bounds, so I'm not going to check them here, but I am still going to check them here because we'll be adjusting the index when we make further calls of this flood fill. This wasn't a flood fill. I'm going to call it just fill, I guess. It doesn't matter as long as it's called something else. Actually, no, I can call it flood fill. That's fine, because then it's got this different function signature, so it's overloaded. It's a little different. Okay, so the original color is the color at the requested position. So it's image SR for row and SC for column. The new color that we want is we're gonna set the image to it. So image SR SC is going to be color, and then we're gonna recurse. So we have to do 4 neighbors. I guess I'll just call it 4 times. It's not like pretty, but I can't think of like a better way. There probably is one. I just don't know of it. So it's gonna be image SR. I'm gonna set this up and then I'll make adjustments. So color original. We're gonna do that 4 times. Once for each of the 4 neighbors. So now how do we do the neighbors? We want one that's, let's say, to the left. And then, sorry, to this is row. So this is one above, one below, and then one to the left, and then one to the right. So those are our 4 neighbors. And that should do it for this. And oh, we'll return the image. And with this ampersand, it means we're passing it by reference, so the image will be modified, and we don't need to explicitly get it back. So that should be good for this. So this is the section of doing work. This is the section of recursing, and there's no base case section. Here we do need a base case because this function itself will actually be recursive. So if 0, 0 is greater than SR, or 0 is greater than the column, or SR is greater than or equal to image dot, and this is the rows, so this is just image dot size, or the column is greater than or equal to image, the first one of the rows size, or there's other things too. So for example, if we're being called on a cell where the color is different from the original. So for example, if we flood, and then we find ourselves here, 0 is different than 1. So we don't want to continue recursing. We want to exit. So if orig, no, it would be this image, the row, and the column is not equal to original. Then we would return. All right, so that's our base case. Now we do work. Image row column equals color. Easy enough. And then we recurse. So for this, it's gonna be this again. I hate to use copy paste. Can't. It's gonna. I would just be typing out the same thing again, this is why I was kind of I don't like doing the setup and then call function here, like with a separate one with the signature that we want. But computationally, this makes the most sense. It just has this chunk being pretty much copy pasted, which I'm not super happy about. But I think this is a safer approach than trying to somehow adapt this to be the one that you recurse with. Yeah, so let's do an example, and then I'll talk about time and space after. All right. So input is this, and we're starting at 1, 1 with the color is 2. So 1, 1, this is our starting point. Color is 2. I'm trying to think of how I want to represent this stack. So I guess I'll do it by indexes. Yeah, I'm gonna try and write it out as like a stack. So first we're calling on 1, 1. That's not like in a stack frame yet, but we're starting there, I suppose. Oh, another thing to note is like, okay, so this check here, this is what's going to take care of if we've already called on a particular cell as well. So this also gets our visited. So for example, say we flood fill this and then we wind ourselves up here. Well, when we check this again, we're going to see, oh, it's a 2 now. It's not 1. Therefore, we're not going to continue on it. So this is also taking care of our visited step. All right, so 1, 1, we made that 2. I guess yeah, okay, I should write this out. Output, no, that's not output. Let's start with the input image. Input. Okay. All right, so we're starting here. 1, 1, our color is 2. So we start there. We're gonna first, we're gonna remember 2. So we got this 2 saved off, and then we change it. And then we're gonna go on the one above. So now we're gonna we're gonna move to, this is 0. This is row 0, column 1. 1 above. Oh yeah, this is gonna get real hard to follow real quick because of all the recursion. All right, so we check the bounds. This is not, neither of the indices are negative, and neither of them are bigger than the number of rows or columns, and 1 does match the original. So we're gonna change that to 2. And then we're gonna recurse on its 1 above, which we're gonna see that the row is now gonna be negative. So then we'd X out of that. So then back to this, we're going to look at the one below. So that's also going to be 2. We're going to see 2 is different from our original value of 1. So then we're going to exit out of that. And so now we're looking 1 to the left. So we're going to look here. We're going to see, okay, so we were at 0, 1. So now we're going to 0, 0. And I'm going to put L for we went left to get there. And for this, that was our, we went up to get there. All right, so 1, that's equal to our original, so we're going to change that to 2. And then we're going to recurse on its upper neighbor, that's negative. We're going to go one below. And so we're going to go here. We're going to change that to 2. And we're going to recurse on, okay, we'll write that down. So now we're at row 1, column 0. And we went down to get there. So then we're going to look at its upper neighbor. That's not, doesn't match the original. We're going to go 1 down. So this, we're going to go there. And then that, so yeah, we'll change it. And then we'll recurse on its upper neighbor. We'll see that doesn't match 1. We'll go 1 below. We'll see that's greater than, we'll see that's equal to the size of the number of rows. And so we'll X out of that. And then we'll go 1 to the left. We'll see that that's a negative index. And then we'll go 1 to the right, and we'll see that 0 does not match 1. All right, so then we're going to pop that off the stack, and we're going to go back to 0, 0, actually. Wait, that was 1, 0. Oh, no, so we were at 2, 0, and we went down to get there. So this is what we're going to pop off the stack. So now we're back at 1, 0. This is this. And we went down to get here originally, so we need to resume from, okay, we're going to look to the left. That's a negative index, so that's X'd out. 1 to the right, we'll see that 2 does not match 1, so then we'll X out of that, and we'll pop that off the stack there. All right, we're back at 0, 0. So we went left to get there, so now we're going to look, so that was this. So now we got one more line, we're going to look right. We're going to see that 2 does not match 1, and so we'll pop that off the stack because that's the end. All right, so now we're back at 0, 1. And we went up. So that was let's see this. So now we're here. We're going to look down 1. We're going to see that 0 does not match 1. And so we're not going to do that. We're going to look to the left. We're going to see that 2 does not match 1. What did I miss? Did I miss something? There should be, we need to get to this, and that's going to be coming from this row 0, column 1. Did I forget to write that? Row 0, column 1. Oh, okay. Yeah, no, I know what happened. I didn't write down 1, 1 on the stack. So actually, I was looking at the wrong place. So here, we went up to get there. So now we're going to look to its right. Oh, sorry, 1 below. So we're going to look below. This is 2. 2 does not match 1, so we don't do that. Now we're going to look 1 to the left. 2, again, 2 does not match 1. Now we're going to look 1 to the right. That's this guy. So we're going to put that on our stack. So now we're at row 0, column 2, and we went right to get there. All right, so we're going to do work, which is going to change the color. We're going to make that 2. And then we went right. So that means that's it. There's nothing else to do there. So we pop off the stack. There's no more recursive calls. Okay. So back to this. So we just finished going right, meaning that is also the last of it. So we're going to pop that off our stack. So we got to this line here, and we're going to return our image. So this is our output image, and this is what we expected. That's what we wanted. Cool. Okay. All right. Let's talk about time and space. Suppose we want to flood fill the entire square. Say it's all 1s, and we want to change it to all 2s. That makes it, let's see, they denote it as m by n, so I'm gonna put the runtime in terms of that too. So it's m times, it's mn time, and so yeah, m by n. So yeah, it's basically linear on the input size if the input size is, this product. And the space is gonna be the same. The reason for that is, okay, we're gonna end up recursing at some point on each one. Let's see, first it goes up and then down, left and then right. On ones that we don't do a follow-up recurse on, so if it's one that we're not going to do any work on, one of these conditions hit, we're going to have, for sure, at most 4, but realistically probably 1 or 2, but definitely at most 4. I don't think 4 is actually possible, but there's only 4 calls, so at most 4 recursions per neighbor, and we're not going to do another 4 if they don't meet particularly these bounds conditions, or if it doesn't match the original. So if it's already been changed, where it's not going to add more to it. So that still puts us at most 4 stack frames per cell, and 4 is a constant, so that still leaves us at constant space per cell, meaning that it's still going to be O of mn space, time and space. Right, so okay, we did an example. We talked about time and space, the work in each call. So this is all constant because this is just setup. This is the one that varies per runtime. This is constant, and this is constant, and we're gonna end up calling this potentially. For sure, this is gonna run at most once per cell. It's the stack frames, like this briefly is the part that will be kind of redundant, maybe 4 times per cell, but this is only going to happen once per cell because that's the only time that we don't hit one of these exit conditions. Uh, you know what? I missed. Did I accidentally erase a line? I'm missing the 4th call on a neighbor there. We need 1 to the right. Okay. I don't know if I accidentally erased that, but I think that's good. That's good. That should do it. Linear time and space on the input size. And yeah, let's just go ahead and run it. What I get? Address error. SR. Stack Overflow. I wish it would just tell me where. Give me a line number. 22? No. All right. Okay. What's going on? So if 0 is greater than, so if the row, I'll write that different to make it, so SR 0 or SC less than 0 or SR is greater than the size or SC. It might be this. I'm gonna add a condition to that and see if that's what it needs. Although I can't imagine, why would you have like an empty row with nothing in it? That would be weird. Uh, instead of checking there, I'm gonna check here, I guess, for edge cases. So let's see if image dot size. So if there are no rows, then we're gonna return. Okay, is that gonna do it? Runtime error. Yes, I got nothing. I don't know what's going on. So I figured it out. There's an edge case that I didn't account for, but it talks about in this second example here. So in this case, the starting pixel, if the starting pixel is already the color that you want, you'll hit this base case condition doesn't account for that. So if like the color and the original are always the same, then you're never going to change anything and you're never going to hit the condition and you'll recurse infinitely. So that's what I was running into. So this is a special case where if your starting pixel is already the color that you want, you just don't do it. So that's something, the way to solve that is for accounting for it here. So if image SR SC is already equal to our color, then we just return. That's how you account for it. Uh, and I'll talk about some of my debugging process that I did while the video was paused. I put this print statement here to track the number of recursions that were happening. I saw that, okay, it was getting called, and I saw that, for example, position 0, 1. So 0, row 0, column 1. This was getting called more than twice. I can understand looking at it, particularly this print statement was in the section where work happens. Work should never happen on it more than once. And I was seeing it at least, 3 times within a few lines of printing. So that was part of the issue. So there was that. So there's something to do with these base cases, like what was going on. And yeah, so that was something that I missed. And something to keep in mind is this definitely falls under an edge case that I should have foreseen. Lessons learned, and hopefully you guys don't make the same mistake when it comes to crunch time for you. Anyway, so just to show you, this is gonna be accepted, hopefully. Yeah, so that works. And then this was the case that was recursing infinitely before. Let's go ahead and submit and call it a night. Cool. And then mark it off there. Thanks.